Hello, Dr. Bergen. Joseph Farab here. I'm here to do the Unit 2 case connections video. And the two cases that I chose were case 1 and case 2. So we'll get started right on it. Case 1 talks about pyruvate kinase and how there are different forms of pyruvate kinase. And the question asks, under normal conditions, describe all the ways in which pyruvate kinase is regulated in the cell. So pyruvate kinase can be inhibited by ATP, alanine, phosphorylation, glucagon, and epinephrine. The way that ATP inhibits pyruvate kinase, and similar with alanine inhibiting pyruvate kinase, is that a enzyme's catalytic activity is less likely to move forward a reaction if there are more products than substrates. So in the case of ATP and alanine, ATP, which would be indicative of high energy states in the cell, and also ATP is the molecule that we're creating via substrate level phosphorylation from ADP, we would not want to work against a higher concentration gradient of ATP molecules. Similar with alanine, pyruvate can be converted into alanine and alanine back to pyruvate via transamination. Therefore, they're similar, the alanine and pyruvate, and looked at as such by the pyruvate kinase enzyme. So if there's large amounts of alanine, it's semi-indicative of large amounts of pyruvate. And just as I mentioned before, pyruvate kinase would not want to work against a higher concentration gradient. With epinephrine and glucagon, both of those hormones increase gluconeogenesis pathways and shut down glycolysis pathways. That's how those two hormones inhibit pyruvate kinase activity. And protein kinase A also phosphorylates pyruvate kinase, and adding a phosphate to it decreases its activity. As far as activation goes, pyruvate kinase is activated by, fructose 1,6-bisphosphate through allosteric activation. And the way that occurs is fructose 1,6-bisphosphate has to be catalyzed by aldolase into glyceraldehyde 3-phosphate and dihydroxyacetone. However, the delta G0 prime of that reaction is very positive, which makes the cell less likely to move that reaction forward. So as the fructose 1,6-bisphosphate accumulates, it allosterically activates pyruvate kinase. And what pyruvate kinase does is it then starts moving forward all of the glycolytic intermediates that came before it. It will move its phosphenylpyruvate, turn it into pyruvate, and this then decreases the amount of products post aldolase. And now aldolase is working against less of a concentration gradient, which makes the likelihood of the reaction more favorable, and it then is able to catalyze fructose 1,6-bisphosphate through a means of feed-forward regulation. In addition to the fructose 1,6-bisphosphate, insulin can also improve or activate pyruvate kinase, and that's through a long cascade of processes, but The latter of those processes involve protein kinase A activating phosphofructokinase 2. And what phosphofructokinase 2 does is it converts fructose 6 phosphate into fructose 2,6 bisphosphate. Phosphofructokinase 2 is able to become active once protein kinase dephosphorylates it pretty much. So upon dephosphorylation of the phosphofructokinase 2, we have our fructose 6-phosphate converting into fructose 2,6 bisphosphate. Now, fructose 2,6 bisphosphate is then going to enhance the activity of phosphofructokinase 1. And phosphofructokinase 1 is going to convert that fructose 6-phosphate into fructose 1,6 bisphosphate. And as I pretty much mentioned not too long ago, that fructose 1,6 bisphosphate is going to allosterically activate pyruvate kinase. So it's a long backtracking, but pretty much they're correlating and increasing activation. For the second part of the question, it talks about pyruvate kinase M2 and pyruvate kinase M1. The question says, the logic seems counterintuitive for glycolytic tissue to have pyruvate kinase M2. And what is the rationale for this mechanism of pyruvate kinase M2? And the second part of the question, which I'll be repeating later, says, what other pathways may cancer cells be diverting substrate to? So the reason for the cancer cell to utilize pyruvate kinase M2 and favor that over the quicker acting or more active pyruvate kinase M1, is because the slower acting pyruvate kinase M2 is going to cause a larger accumulation of glycolytic intermediates to amass or form within the cell. And with the cancer cell, its main goal is proliferation and building up cellular mass. So with it having a large accumulation of glycolysis intermediates, it can use those and turn them into macromolecules, which can support its cell proliferation. Pardon me. My apologies. So with the pyruvate kinase M2 being slow, causing an accumulation of glycolysis intermediates, the glycolysis intermediates being beneficial for the main objective of the cancer cell by providing a bunch of macromolecules that can be utilized to promote cellular growth. So as far as the second portion of the question, it says, I'll restate, what is the reason for this mechanism and what are the other pathways that cancer cells may be diverting substrate to? So as I said, the cancer cell wants to promote cellular biomass and proliferation, so I believe that it's going to be diverting these glycolysis intermediates to pathways such as the pentose phosphate pathway to form more nucleic acid synthesis. I presume also that the cancer cell will utilize the pentose phosphate pathway to produce more aromatic amino acid synthesis. And It'll also divert substrates towards the creation of fatty acid synthesis, all to which are meant to promote further growth of the tumor cell. So that wraps up case 1, and we'll go to case 2 here.